Now in this video we're going to look at rigid body movement and well, how to see it and how to remove it. If we have a look at our y variable, actually our delta y variable, or v variable as it were, you can see at this image number 90 we've got about 2.5 millimeters of movement from the top there, about 8 millimeters of movement down the bottom there. The machine that we tested this on, actually the top is held steady and the bottom moves down, so this 2.4 millimeters of movement is actually stretch. So if we have a look further down, 2.8 millimeters, 9.8 millimeters. Now actually some of this movement as well could actually be the machine, could be compliance in the machine too. 3.8 millimeters to 13, 3.9 millimeters to 14, 4.3 millimeters to 18. We're starting to get some failure here. And down to 3.9 millimeters again, and 20 millimeters down here. Now at this point, we haven't quite failed yet, but it's very nearly failed. And so yeah, that number there has actually gone down because the force inside the specimen is actually reduced. So yeah, that's pretty cool. Until we finally see our final image, which is the specimen completely failed. 3.6 millimeters there, so that's entirely stretch, and 24.6 millimeters there. So to remove our rigid body motion, we want to go to Data, Post-Processing Tools, Remove Rigid Motion. If you use an average transformation, you sort of select a series of boxes like that and you call the average of that 0. We can do that, that's fine. Or we can just choose one point and go there and say, hey, that's fine. What you have to be careful of, which I just discovered in making a draft for this video, is that you want to be very careful that you choose a point that doesn't actually disappear from the image. So if I was to choose this point here, that would disappear from our area quite quickly. So I'm going to choose a point a bit further up here. We get about 25 millimeters of total movement, so I'm going to estimate more than 25 millimeters above here, so I'm going to say that point there. So we hit compute and successfully processed all our data. So now it is saying that these points around here are 0, and this top part has actually moved upwards by 20 millimeters relative to that point. Makes sense. We have a look at earlier images, and you can see 14 millimeters versus minus 0.8. That's alright. But yeah, so this data is actually a little bit more meaningful in the sense that we can look at our data, we can look at the colors on here and we can say a bit more clearly, okay, we've had 12 millimeters of displacement. I mean, there's a little bit of extra there, but you can ignore that. 16 millimeters, whoops, and onward. All very good. One final thing to note with, just while we're on this subject, it's a little bit unrelated, but it's just a little personal preference of mine. Up here, our color map. By default, it chooses a clockwise color spectrum. I don't really like that because red eventually goes back into purple, which goes back into blue, and it's not really crystal clear. I personally like a temperature map. You can see, yeah, it basically goes from cold to hot, and yeah, there's no way you can come back around to there. So to me, I just find that these colors are just a bit more nice, a bit clearer. So take that for what it's worth. Thank you.